Alrighty, so let's just have a quick look to see what's in this unit. This, as well, is a fairly short unit. I would expect a test in approximately 2 weeks. There is a 2-day lab that will start tomorrow. It's too bad it's going to tie up over the weekend, but that's just the way it is. So, you will explain qualitatively why an object moving at a constant speed in a circle is accelerating towards the center of the circle. You will discuss the centrifugal effects with respect to Newton's laws. You will draw free body diagrams of an object moving in uniform circular motion. You will experiment to determine the mathematical relationship between period and frequency in one or more of the following. Actually, we're going to do them all. You will derive an equation. Oh, there should be cheering when I say that. We'll spend a day deriving equations. It'll be a lot of fun.
Oh, like we did last time. Yeah. To use the equation.
I'll be deriving. You'll just be along for the ride.
Okay.
Oh.
Derive an equation for the constant speed and acceleration of an object moving in a circle. Those are the ones we're going to come up with. And you will solve problems for an object moving with constant speed in a circle using those formulas. And there are 3 problem types. They are horizontal motion, vertical motion, and banked and unbanked curves. I guess that's actually 4 types.
Okay.
Okay? And is there something on the back? No, don't think so.
It's just always different how more space.
Oh, it's more spaced out.
Another time types on mine.
Yeah.
Like a flat curve is like a road kind of thing, like the track, whereas a bank curve would be like on a NASCAR kind of thing. What do you need, Josh? Oh, really? Didn't realize that. Josh says we don't have the problem types on your sheet. I didn't realize that.
It says problem types. Oh, it just says the word.
Oh, okay. Question number 1 says, you are spinning a bucket attached to a string in a circle above your head. This is all pre-ahead. This is to find out, to get you thinking. Hello, Mr.
How one's come to visit you yet?
No.
Okay, so I've got a couple coming this way.
Okay. To be honest, I kind of... Okay, so the question is, you are spinning a bucket attached to a string or a rubber stopper, like so. A what force holds the stopper in a circular path? Is it a centripetal force, a centrifugal force, or C, I don't know, which I will tell you is not the correct answer.
I mean, it's the one I know for sure.
It might be true for you.
Are we just going to keep going? Like through all the
Yeah, and it's okay. We're going to explain this. This is just my way of getting you thinking about centripetal forces. Okay? Centripetal forces and centrifugal forces. Okay, Josh, come on, man. Okay. In a washing machine, during the spin cycle, the force is on the what? Causing the water to be separated from the clothes.
What?
In a washing machine, during the spin cycle, the force is on the water, the force is on the clothes, or again, I don't know.
If it was water, it wouldn't be very good sentence structure to say water again right after. So probably
The force is on the water, causing the water to be separated from the clothes. Nothing wrong with that?
No, it's on the clothes. It's on both. It'd have to be on both.
Oh, well, let's say that.
That's causing everything else to move with it.
I'm gonna say clothes because it's heavier.
Yeah, it'd be weird if the force is on the water, causing the water. They could just say causing it to be separated from the clothes.
It's okay to be wrong here. This is learning. It's okay to be wrong. You learn from mistakes.
I do not learn from mistakes. I get
This is not a record. This is not an assessment to see what you know. That's right. It doesn't matter. It's okay to be wrong.
Can you do sick yo-yo like that circle?
A tube has been placed upon the table and shaped into a 3/4 circle. So the table is like this. Okay? A golf ball is pushed into the tube at one end at high speed. So the ball is pushed in here at A.
How high speed are we talking?
Oh, like high speed.
Like high enough to shoot it off the ground?
Yes. If it wasn't the correct angle. Okay? Like we'll say like, I don't know, 15 meters per second. Fast. The ball rolls through the tube and exits at the opposite end. Describe the path of the golf ball as it exits the tube. Does it go, as it comes out here, does it go up and complete the circle? Does it head out at C at something like this, or does it go straight across the table at B?
I'm gonna say C. Because it wants to complete that circle, but it's not.
No, but it gets let out hopefully halfway through.
Yeah, but maybe this one.
Yeah, well, I think it push
The force.
it's letting it.
Use the force, right?
So it's like this, it's like.
No, you're not listening. You guys can show that. That's what I did. It's the truth.
Well, maybe.
I just like how you guys are actually discussing this.
Maybe it would.
Oh.
Maybe it would. That's what because
Exactly, but it's for each.
it's going around the circle.
For you two. Tangent to circle means that it goes like in a straight, you know, like when we did tangents in grade 11? In a straight line, instantaneous slope?
Would it go up
Okay, Mr. Bennett is spinning a rubber stopper at a constant rate of 3 revolutions per second. Like a thing for a test tube, a rubber stopper.
that came off the ground?
I've actually let go before. I've let go and tried to hit people before. And I've tried to miss them, and I've missed and actually hit them.
What?
It was you, wasn't it? Didn't I hit you?
Try it right now.
Yeah. I accidentally hit Hannah. She's okay though. I won't do it again. Okay? No, you can't. The rubber stopper is accelerating. True or false? Constant 3 revolutions per second.
I feel like it's
False.
Is it true or is it false? Is it accelerating?
If it's a trick,
it just seems like it's
You have teed it up on your butt, on your foot.
is it gravity still affecting it?
Gravity is always in effect. Can't turn gravity off. But when you're driving down the highway at a constant speed, are you accelerating downward?
It's trick. It's real. It's real.
That's true. There's no normal force, that's true here.
That'd be like the centrifugal force.
But the force over it gets stopped.
Mr. Bennett is still spinning the rubber stopper. What direction is the force on the stopper? Tangent to the circle means like this. Like A would be in, if this would be A, this would be B, that would be C. Tangent to the circle. Which direction is the force? Have I seen what? Yeah. 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 That's the angular momentum. I used to have a big bicycle tire that you could do stuff like that with, but someone stole it on me.
I didn't.
You spin it and do weird stuff with it. When you're driving your car and make a left turn, friction between your tires and the car, between your tires and the road, cause the car to move to the left. So it is friction, they're saying, that makes you go left.
Friction. Yeah.
Looks like
If there was no friction, give it gas between the ground.
Whoa. Wait, we're on 6?
Is that you last night? Oh. And I kind of moved over to the side. Is that you?
Okay, what was
Okay, ready for some answers? Well, I'm still waiting on a couple here.
Oh, no, 5 would be going out.
Okay, so I'm going to read the handout, and you follow along with the questions as well. And we should be. What was the first question? All right. Okay. Okay. So the handout says, if you whirl a tin can on the end of a string, you find that you must keep pulling on the string. You pull inward on the string to keep the can revolving over your head in a circular path. A force of some kind is required for any kind of circular motion. Any force that causes an object to follow a circular path is called a centripetal force. Centripetal force. It's highlighted there for you. Centripetal means center-seeking or toward the center. The force that holds the occupant safely in the rotating carnival ride, which we don't have a picture of, is a center-directed force. Without it, the motion of the occupants would be along a straight line and they would not revolve. What's that thing that comes to the fair every year where you go in and you stand? What's it called?
G-force.
G-force. And it spins around like this, and then eventually it starts to go like at an angle, right?
Yeah.
And there's that little teeny tiny chain that is there for safety. I am not going on that.
It's so
Is
funny.
that little teeny tiny chain doing anything?
No.
No.
You're gonna hold it on.
No.
Up when you're on the edge. You're off.
It is inertia that keeps you in there.
Could you even like get off the stride?
Inertia will not do. It is a universal law. The little teeny tiny chain doesn't do nothing.
Hey, you know what's really fun? That dragon one.
Okay, I gotta keep going, you guys.
That one like
There's so much extra noise. Like, I don't mind if you have a question, but like everyone's just constantly talking.
Constant motion. No.
Centripetal force is not a new kind of force. It is simply the name given to any force that is directed at right angles to the path of a moving object that tends to produce circular motion. Gravitational and electrical forces act across empty space as centripetal forces. If you drop something like a thing of sticky notes, gravity's pulling it toward the center of the earth. It is a center seeking to the center of the earth. Gravity is a centripetal force. We just don't realize it because we are currently in it and rotating. Okay? Gravitational force directed toward the center of the earth holds the moon in an almost circular orbit about the earth. Electrons that revolve around the nucleus of the atom are held by an electrical force that is directed toward the central nucleus. So all of those are examples of centripetal. I'll get to it. I will get to it. If you let me. Because I'm running out of time. Centripetal force plays the main role in the operation of a centrifuge. A familiar example is the spinning tub in an automatic washing machine. Maybe you know where it is in your house. In its spin cycle, the tub rotates at high speed. The tub's inner wall exerts a centripetal force on the wet clothes, which are forced into a circular path. The tub exerts a great force on the clothes, but the holes in the tub prevent the tub from exerting the same force on the water in the clothes. The water therefore escapes. It's important to note that a force acts on the clothes, not the water. You're exerting a force to keep the clothes moving in the circle, and the water goes out. That's the second answer, right?
Mm-hmm.
No force causes the water to fly out. No force causes the water to fly out. The water will do that anyway, as it tends to move by inertia in a straight line path. Newton's first law, which says objects in motion stay in motion, but it's also in a straight line, unless acted on by a centripetal or any other force. So interestingly enough, the clothes are forced away from the water and not the other way around. Same is true in a salad spinner. When an automobile rounds a corner, the sideways friction between the tires and the road provides the centripetal force that holds the car in a curved path. If the force of friction is not great enough, the car fails to make the curve and the tires slide sideways. The car skids. And Talia said it perfect. She said in the wintertime, when you turn the steering wheel, if there's not enough friction, you just keep going. Straight line, right? So your tires just point you in the right direction, but it's actually friction that pushes you. Pushes you.
Wow.
It's kind of a weird, next time you make a turn, think about it, and friction is pushing you. It's kind of a weird thing to think about. Okay, centripetal and centrifugal. I've got 15 minutes, I really gotta go. In the preceding examples, circular motion was described as caused by a center-directed force. Sometimes an outward force is attributed, or comes along with, circular motion. This outward force is called centrifugal, with an F. Centrifugal means center fleeing, or away from the center. Okay? In the case of the whirling can, it's a common misconception to state that a centrifugal force pulls outward on the can, okay, or the rubber stopper. Where's my rubber stopper? Okay? So when I do this, there is a force on the rubber stopper, but what direction is it?
On the inside?
It's in. I'm pulling in. How can I exert an outward force on the stopper? The only way to exert an outward force would be if I
Pushed it.
and can you push on a string? You can, but it doesn't go very good, does it? You can only pull.
That's
So the force is towards the center, centripetal, not centrifugal. Now, if you were a little teeny tiny miniature, you know, like in Honey, I Shrunk the Kids or something like that, and you were on a rubber stopper, would you feel that outside force?
No.
Yes, you would.
You
You would feel like when you're in the, what's it called, G-force? When you're in the G-force, don't you feel like your face is doing this?
Yeah.
How come?
So that's the other.
Is there a force pulling you out?
But that'll stop.
No, there's not.
There is no force pulling you out. That is inertia. Do you feel the metal cage with that little teeny tiny pad pushing you in towards the center?
Yeah.
Yeah, but you feel like you're going out like this, right?
Yeah.
And you're literally your face.
Well, what the heck?
Right?
I
But
don't
it's
know.
not a force outward on you, it's a force inward. Your body's trying to go in a straight line and the cage is going, you're coming in a circle with me, buddy. Okay? Listen carefully. If the string holding the whirling can breaks, it's commonly stated that a centrifugal force pulls the can from its circular path. So if I were to let go, no?
Yeah, do it.
I know I'm afraid to do it now because I didn't.
Just throw it over
Everyone
there.
brace
What
yourself.
if the string broke,
Did you actually do it?
right? It would go flying through the air like that. But is it a centrifugal force that pulls it out? No, it is in fact inertia that keeps it going. It is inertia that keeps it going. Right?
Physics is a lie.
When the string breaks, the can goes off at a tangent straight line path. Why? Because no force acts. Remember, objects in motion stay in motion. So when it's spinning around, and then at this point right here, if I let go, I remove the force, and so what does the object do?
Go that way straight.
Stays in motion and goes
To tie.
tangent, right towards path. Right? Objects in motion stay in motion. That's what I'm getting at. Suppose you're in the passenger of a car that suddenly stops short, like stops quickly. You pitch forward against the dashboard, right? Like we're driving the big, I'm Miss Frizzle, I'm driving the big bus, I hammer on the brakes. What do you guys all do?
Go forward.
You go forward. How come? Inertia, because objects in motion stay in motion. The car stops, you go forward. When this happens, you don't say that something forced you forward. You know that you pitched forward because of the absence of a force which a seatbelt would have provided. Similarly, if you were in a car that rounds a sharp corner to the left, if I'm in the Magic School Bus and I crank the wheel to the left, you guys all go
No way.
That way.
to the right. But do you really go to the right?
No.
No, the bus goes left, you go straight. Right? Okay.
Wow. I
No
don't
way.
like. I don't like. How
You tend to pitch outward to the right, not because of some outward or centrifugal force, but because there is no centrifugal force holding you in a circular motion as a seatbelt would provide. The idea that a centrifugal force bangs you against the car door is a misconception. It's not true. So, when you swing a tin can in a circular path, there is no force pulling the can outward. Only the pull by the string acts on the can and pulls the can inward. The outward force is on the string. Okay, that's a very important distinction. The force on the rubber stopper of the can is in, but is there a force on the string? Yes, there is, and it is outward.
Yeah.
Now, where does this force come from?
Inertia.
Inertia. No, it's centrifugal, but nothing is providing it. Like, I'm providing the force, right? I'm pulling it inside. What's providing the force on the string? Outward.
The inertia.
Stopper, but it's inertia, right? It's like a fake force. Fake
What?
news.
Fake news.
Fake news.
Now, suppose there's a ladybug inside the whirling can. The can presses against the bug's feet and provides the centripetal force that holds it in a circular path. The ladybug, in turn, presses against the floor of the can, but neglecting gravity, the only force exerted on the ladybug is the force of the can on its feet. From our outside stationary frame of reference, we see there is no centrifugal force exerted on the ladybug, just as there was no centrifugal force exerted on the person who lurched against the car door. The centrifugal force effect is attributed not to any real force, but to inertia, the tendency of the moving body to follow a straight line path. Try telling that to the ladybug. Okay, where's my stop? There's a classic movie. It was put out in 1968 or 69. It's called 2001: A Space Odyssey. It's supposed to be like what life was like in the year 2001, which interestingly enough is that the year you guys were born. 2000. So yes, it was like all the rage back in the late 60s, early 70s, because this is what
Flying
it's supposed to be, right? Well, they had a space station, which we have, right? In the space station, they had this big giant wheel, and there's this really famous scene where the guy's going for a run, the astronaut, and he's running in this big, you know, like a hamster wheel?
Yeah.
Okay, so it's kind of like a hamster wheel. So he runs up the side of the wall and goes all the way around the wheel because it's spinning just enough that it provides enough G-force that it sort of holds him in place. Okay. What? I don't know how they did it in 1969. It's not computer generated. I don't know how they did it. They must have done it all with like camera angles and built a big giant hamster wheel, or I don't know how they did it.
Impressive.
It's a good question. Okay, I got to get through this here.
Could it actually be done?
It's a little bit fake. It's got to be spinning pretty fast. It would have to be huge. Have you guys ever seen the TV series about 100?
Yeah.
Okay, and they have like the arc, right? And they're all walking around up there in space. Not very reasonable, right? Not very lifelike. They said it's because it's spinning, but it would have to be giant. They're just walking around like it's like on Earth. Just too hard to film any other way.
I don't like that show.
I mean, it used to be good, yeah. Our view of nature. Now we need to talk about frame of reference, and I gotta hustle. Our view of nature is very much influenced by the frame of reference from which we view. When we sit on the seat, hang on, Johnny. Just chill. Johnny, please. When we sit on the seat of a fast-moving train, we have no speed at all relative to the train, but an appreciable speed relative to the reference frame of the stationary ground outside. We've just seen that in a non-rotating reference frame, the force that holds an object in circular motion is a centrifugal force. So we are all in this non-rotating reference frame, and we're looking at me spinning it above my head. Don't hit myself. For the ladybug, the bottom of the can exerts a force on its feet. No other force was acting on the ladybug. But nature seen from the reference frame of the rotating system, in other words, if you're inside it, is different. In the rotating frame, in addition to the force of the can and the ladybug's feet, there is a centrifugal force that is exerted on the ladybug. So centrifugal forces exist, but only when the observer is inside the system. Okay, you have to be inside it to observe it, you have to be able to explain it. Centrifugal force in a rotating reference frame is a force in its own right, as real as the pull of gravity. However, there is a fundamental difference. Gravitational force is an interaction between one mass and another. The gravity we experience is our interaction with the Earth, but centrifugal force in the rotating frame is not part of an interaction. It is like gravity, but with nothing pulling. Nothing produces it. It is the result of rotation. For this reason, physicists rank it as a fictitious force and not a real force like gravity, electromagnetism, and the nuclear forces. Remember those four fundamental forces that were the very first thing in grade 11? Nevertheless, to observers who are in a rotating system, centrifugal force seems to be and is interpreted to be a very real force. Just as from the surface of the Earth we find gravity ever present, so within a rotating system, centrifugal force is also ever present. Now that's a lot to digest, and normally I spend much more time on that. Okay. How about you read those questions? We'll try them first thing tomorrow. We're going to do the lab. The lab is usually a 2-day thing. We'll start, if we can get started right away, we might actually be able to get done in 1 day, but it's unlikely. You will be doing a lot of this tomorrow.
No, lab day one.
Lab day 1, okay? And you will have to wear safety glasses. That's the last thing to wear. Okay? I should probably wear a helmet. Is that it? You guys have any other things in your handout? You have a question? Oh, okay. That one is, no, it is B. Because objects in motion stay in motion, right? There is no force putting it up. Yeah, that one is B. This one here, is this true or false? True. Why is it accelerating? Because it's changing Direction. Oh, if you're changing direction, you are, right? What's direction is the force and the stopper? The answer is A, towards the center. Johnny, do you realize I'm still teaching here?
Yes.
Friction. Is this true? Yes, it's true. Okay. Now I'm done, Johnny.
Yeah, yeah.